Mixing and flocculation. Mixing, dispersing coagulants into the water is a critical step in the treatment process sequence. Mixing of chemicals may be accomplished by rapid mixer or inline mechanical mixer. The velocity gradient is one of the main parameters used in designing mixing systems and is determined using the following equations. Rapid mixing. Disperse chemicals uniformly throughout the mixing basin. Allow adequate contact between the coagulant and particles. Rapid mix tanks. These are necessary for dispersing the coagulant and coagulant aid into the water. Stator blades and/or baffles along the sides of the walls should be used to prevent vortexes from forming. Either square or circular tanks may be used. This is a sample of a rapid mixing. Flocculation involves slow stirring or mixing of the destabilized colloids to promote particle aggregation and removal during subsequent settling operations. Mixing cannot be too intense, as the fragile flocks will share into small fragments and not settle properly. Primary types of device used in water treatment. Paddle wheel flocculators. Vertical turbine mixers. Paddle wheel flocculators rotate from 1 to 5 RPM, whereas vertical shaft turbines rotate from 10 to 30 RPM. Design criteria for horizontal shaft paddle and vertical shaft turbine flocculators. Paddle wheel flocculators may use horizontal or vertical shaft, but typically, horizontal shafts are preferred at conventional water treatment plants. A detention time of at least 30 minutes is recommended, with a flow-through velocity no less than 0.5 feet per minute and no greater than 1.5 feet per minute. In recommended standards for waterworks, engineers are encouraged to use tapered flocculation to produce large, dense floc. Tapered flocculation employing 3 separate compartments, each at a different velocity gradient, is normally practiced so that a dense, good settling floc is produced. Typical G values used in the first, second, and third compartments respectively are 50, 20, and 10 seconds. The velocity gradient varies from 10 to 100 and the GR parameter varies from 104 to 105. The power dissipated in the water by a paddle wheel flocculator is calculated using the following equation. Normally is 0.70 to 0.80 of the paddle velocity. The velocity of the paddle blade is calculated from the following equation. Vertical shaft turbine flocculators. In new water treatment plants and those that use direct filtration, vertical shaft turbine flocculators are typically used. This type of flocculator has an impeller attached to a vertical shaft that is rotated by an electric motor. There are different types of impellers that use either radial or axial flow mixing. Important design parameters for these types of flocculators include power number, effective tank diameter, and diameter to effective tank diameter ratio. The power number is calculated using the following equation. The effective tank diameter is determined from the following equation. The D over T sub E ranges from 0.3 to 0.6, but a value of 0.4 to 0.5 is recommended. Sedimentation. Sedimentation is a physical water treatment process using gravity to remove suspended solids from water. Solid particles entrained by the turbulence of moving water may be removed naturally by sedimentation in the still water of lakes and oceans. Gravity settling is the major unit operation used for removing suspended solids. Sedimentation is considered a unit operation involving solids-liquid separation using gravitational force. If the raw water contains turbidity greater than 1000 NTUs, Pre-treatment in the form of plain sedimentation is typically accomplished before proceeding to coagulation flocculation processes. Surface water will contain turbidity in the form of colloidal and suspended solids that must be removed from the water. If the raw water contains turbidity greater than 1000 NTUs, pre-treatment in the form of plain sedimentation is typically accomplished before proceeding to coagulation flocculation processes. Discrete settling. Discrete settling, which occurs in grate chambers at wastewater treatment facilities, can be analyzed by calculating the settling velocity of the individual particles contained within the water. There are that act on a particle as it settles: gravitational force, buoyant force, and drag force. Two types of settling that are typically encountered: free settling and flocculent settling. Free settling. Free settling is observed when there are discrete non-flocculent particles whose size, shape, and specific gravity do not change with time as they settle. Particles settle as individual entities and there is no interaction between particles. Terminal settling velocity of a particle is derived in this section. For spherical particles, the volume and cross-sectional area are calculated using the following equation. Settling velocity equation. Flocculent settling. Flocculent settling occurs in primary clarifiers and during settling of coagulated water and wastewater. As flocculent particles settle, their size, shape, density, and settling velocity will change with time. Newton's law or Stokes' law cannot be used for modeling flocculent settling. Percent removal is calculated using the equation below. This equation may be used to calculate the percent removal for any specific parameter just like COD, BOD, TSS, and etc. Figure 6.22 shows settling column and settling trajectories for flocculent suspension. Equation 6.97 is used for calculating the overall percent removal of solids that may be achieved at a given detention time. Flocculent settling laboratory procedure. Flocculent settling column analyses are typically performed in a Deere PVC column with sampling ports spaced approximately 6 inches apart. A column on the order of 5 to 6 feet is used. The steps involved are listed below. Fill settling column with coagulated water to be treated. Take an initial sample for suspended solid determination. Take samples for each sampling port as a function of time. Calculate the percent suspended solids removals and plot them as a function of time and depth. Calculate overall percent suspended solids removals using equation 6.97 for several detention times. Plot overall percent suspended solid removal versus time. Ideal settling basin. Overflow rate serves as a design parameter used by engineers to determine the size of settling basins, whereas water treatment plant operators regulate the flow through the basin to maintain the proper detention time and overflow rate to achieve optimum solids removal. The overflow rate is a different way of expressing the settling velocity of a particle calculated using Stokes' law. Remember, settling velocity is a function of the diameter of the particle. Overflow rate is normally expressed in units of GPD per feet squared. Theoretically, all particles with a diameter equal to or greater than the particle size specified by overflow rate should be completely removed. Figure 6.23 shows an ideal settling basin with an inlet, outlet, and sludge settling zone. The basis for design of a settling basin is to select a specific diameter particle that will settle by gravity during the time that it takes water to travel through the basin. Under ideal conditions, a particle will travel a vertical distance of h during time. Mathematically, the distance traveled is equal to the rate multiplied by time. This same particle will travel a distance of L in the horizontal direction during the same time as shown in equation 6.99. The horizontal flow through basin velocity is calculated by rearranging the continuity equation, which is shown below. Overflow rate equation. Detention time or retention time. Detention time or retention time is defined as the time that the water remains in the settling basin. Average, typically the Greek letter rather than T, is used to denote detention time. Weir loading rate. The Weir loading rate is defined as the volumetric flow rate divided by the length of the effluent weir. Regulatory agencies sometimes specify weir loading rate that must be maintained in settling basins. Settling basin design criteria. In water treatment, long rectangular or square settling basins are typically used, whereas circular basins or clarifiers are more widely used for wastewater applications. The actual design of a settling basin not only includes the ideal settling zone, but also an inlet zone to distribute equally the incoming water and dissipate velocity currents, a sludge zone in which particles that settle out of solution accumulate and are subsequently removed for further processing, and an outlet zone in which baffles and weirs are used to ensure that no short-circuiting occurs and quiescent conditions are maintained. Overflow rate, detention time, and weir loading rate are the three main parameters used by environmental engineers in the design of settling basins. Table 6.11 provides typical design criteria for long rectangular upflow radial and reactor clarified type settling basins. Knowing the maximum daily flow to the water treatment plant and selecting an overflow rate at the surface area can be determined. Next, the detention time is selected and the depth is determined by dividing the volume of the surface area. The weir loading rate is calculated after laying out the weir configuration. Table 6.11 shows design criteria for settling basins. Figure 6.24 shows photograph of long rectangular settling basin. Long rectangular settling basins are normally have minimum length to width ratios ranging from 4:1 to 5:1, length to depth ratios of 15:1, and bottom slope of 1:600 when mechanical sludge scraper mechanisms are used. Where circular tanks are used, tank diameters of 125 to 150 feet are recommended. For rectangular basins with a length greater than 100 feet or circular basins with a 70 feet diameter or greater, a side water depth of 15 to 18 feet is recommended. Side water depth is the depth of water at the side of the tank from the top of the effluent weir to the bottom of the tank. An additional 1 to 2.5 feet must be added to the SWD to act as a wind barrier and to account for flow variations.